Hi, this is Professor Zygmunt with Physics 371, Electromagnetic Fields. I'd like to give a brief overview of material presented in Section 1.1 of the textbook. My idea is for you to review this material before coming to class, so you'll be better prepared to take advantage of class time. Your to-do list right away, if you haven't done so, is to purchase the textbook for the course, to read the introductory section in Section 1.1, to access course materials in Blackboard, and to begin the first set of homework problems, which I will post. There's just a few for this first assignment. Here's a brief roadmap for the semester. You can see the breakdown of topics. We'll begin with a review of vector calculus, and then the rest of the semester is broken into chunks dealing with electrostatics, first in vacuum and then in matter, and the same thing for magnetostatics. And then the last 2 weeks will begin a treatment of electrodynamics, which deals with time-dependent electric and magnetic fields. Here's our review of vector calculus, and I just want to jump right into it. Vector algebra. These are topics that are familiar to you from previous math and physics courses, but I just thought it would be good to make sure that you're familiar with these things. Vector addition is very simple. We use the component method of vector addition. Each vector A and B here is represented by 3 components in the x, y, and z directions for the Cartesian coordinate system, and when we add the vectors, we simply add their components. Note the use of x hat, y hat, and z hat to represent the 3 mutually perpendicular unit vectors. There's such a thing as scalar multiplication, where we multiply a scalar or a number by a vector, and that's very simple and intuitive. Finally, vector multiplication. How is it that we can multiply 2 quantities that involve magnitude and direction? And it turns out there are 2 different ways to do it. One is called the scalar product, or the dot product. And in this one, we can see that the 2 vectors, if they're drawn tail to tail, as they always must be for this definition to work, they define an angle theta. And so A dot B, the way we read this, is the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. And we can prove that that is also given in component notation by the sum of the products of the x, y, and z components. As with many things in physics, let me just point out that this is commutative. The scalar product is commutative, so A dot B is equal to B dot A. As with many things in math and physics, there's a geometrical interpretation of this scalar product, and we notice what this is if we look at the projection of vector A along the direction of vector B, which is given by A cosine theta. So since the dot product is A cosine theta times B, what we see is the dot product is the product of the magnitudes of one vector and the projection of the other vector along it. In other words, the magnitude of B times A cos theta. And there are many physical quantities that when we define them, it turns out to be useful to do it mathematically this way. More on that later. Then there's the vector product, also called the cross product. This turns out to be a vector, which is why it's called the vector product, and it's given by the product of A and B, their magnitudes, times the sine of the angle, and the direction is indicated by this n hat unit vector, and that direction is given by the right-hand rule, which you should be familiar with from previous courses. In component notation, there's a rather complicated expression for the cross product. You will have to use this in doing some of the homework problems, especially those that involve derivations or proofs. The vector product, in contrast to the scalar product, is not commutative. It's anti-commutative. In other words, A cross B is minus B cross A, because if one were to interchange the A's and the B's in this expression, you see that you would introduce a minus sign. And so, not surprisingly then, A cross B is not the same as B cross A. Another handy way to represent the vector product is to use the determinant of a simple 3 by 3 matrix involving the unit vectors x hat, y hat, z hat, and then the components of vectors A and B. Now, in order to determine a geometric meaning for the vector product, we draw the same tail-to-tail sketch, and notice that if we were to extend each of the two vectors, in other words, from the tip of A, if we apply B, and then from the tip of B, if we head in the direction of A, we define a parallelogram. And the height of that parallelogram is A times the sine of theta. So, A times the sine of theta times the magnitude of B would give us the area of the parallelogram, which means that the magnitude of the cross product is the area of the parallelogram defined by the two vectors. Now, we've talked about how to multiply two vectors in two different ways. What about three vectors, or five vectors for that matter? But let's stick with three for the moment. Can we form a triple product? And do those triple products have any kind of meaning? Well, it turns out, yes, we will run across these in our study of electromagnetism from time to time, and there are two kinds. There's what we call the scalar triple product, because it is actually a dot product whose result will be a scalar. So if we take the three vectors A, B, and C, where C is intended to be oriented somewhat into the page here, we can see that there is a simple geometrical meaning for this triple product that we can deduce if we look at the actual definition. So A dot B cross C, of course, being a dot product, that's the same as B cross C dot A, can also be given by a 3 by 3 matrix, the determinant of which equals this scalar triple product. But think about the dot product, okay? The magnitude of B cross C is the area of this parallelepiped indicated in the sketch. And then dot that into A, well, let's see, B cross C as a vector is in the normal direction, in the n hat direction, perpendicular to the plane that B and C lie in. So A dotted into that vector would involve the cosine of theta. And so A times the cosine of theta is the height of this parallelepiped. So the area of the base times the height gives, of course, the volume. So the geometrical meaning is that this scalar triple product gives the volume of the parallelepiped that the three vectors define. Thus, if we see that this special kind of triple product is the volume, then the order in which these vectors appear should not matter. In other words, A dot B cross C should be the same as B dot C cross A and C dot A cross B. So all three of these are equivalent ways of representing this triple product and getting the volume of this parallelepiped. Finally, what about the vector triple product, A cross B cross C? Well, this is relatively simple to write down, and you will show for homework that A cross B cross C can be written in the form of B times the dot product A dot C minus C times the dot product A dot B. And this is the so-called back cab rule because of the order in which these vectors appear on the right-hand side. You're going to prove this for homework by writing out, somewhat tediously but instructively, the component form of each side of this equation. As far as a geometrical meaning, you probably could think of one, but a natural understanding of it really doesn't come to mind, at least not for me. If you think of something and want to explain it to the class, please feel free. Now, the last thing in section 1.1 in the textbook deals with the transformation properties of a vector. And what we mean by this is, if one has a vector A, in this case, that lies in the YZ plane, where the x direction is perpendicular to this, how does that vector change when the coordinate system changes? If there's a simple translation of the coordinate system, it's probably fairly easy to see that the components of that vector will change in a fairly simple way. But what about something more complicated, like a rotation? If we rotate the coordinate system, the YZ coordinate system, counterclockwise about the x-axis, which is shown here in the sketch, assuming that that rotation is by an amount phi, What happens then is that y becomes y bar, and z becomes z bar. The vector A has not changed. It is invariant. The rotation has merely affected the coordinate system. But clearly in this new coordinate system, the y and z components of A will be different than they were originally. So how are the new components in the bar coordinate system different from the old components? And it's a fairly simple geometrical and trigonometric exercise to show that you can write this out in the form of matrix algebra. So in other words, the components AY bar and AZ bar can be given by the product of a 2 by 2 matrix involving the rotation angle and the column vector that has in it the components of the original vector in the original coordinate system. So you'll be asked on your homework to generalize this to rotation about a different axis and to figure out how to write down this transformation matrix that takes the old coordinates and generates the new coordinates through the application of this rotation. Well, that's all for now. So I'll see you in class.